two contents we are going to discuss. The first one is towards unification of forces, and the second one is nature of physical laws. Okay, these are the two contents of this video. First, let us take towards unification of forces. See, in physics, no, scientists are more concerned about how they want to unify. Okay, they are more concerned about unifying different forces. Okay, different natural forces. No, they want to unify. Okay, that is the principal thrust in physics. Scientists are concerned about this one, unification. They want to know the relation between different forces in nature. Okay, so towards that one, many people have succeeded. Okay, we will list one by one. Before that one, I want to actually give some introduction about unification. Okay, here it is. Unification means existence of relationship between various forces of nature. Okay, that means what is the relationship between various forces of nature? That relationship studying is known as unification. Okay, and some of the highlights made towards this unification is given below. The first one is scientist Newton. Okay, he was very much successful in unifying terrestrial and celestial mechanics. Okay, according to Newton, he tells that the same law of motion and same law of gravitation will apply to both terrestrial and celestial bodies. Okay, that unification was made by Newton in the year 1687. Then comes Maxwell. Okay, in the year 1873, Maxwell told that he showed that electricity, magnetism, and optics they are nothing but electromagnetic waves, and he told that light is an electromagnetic wave. Okay, he took the concept of, I'll write here, he took the concept of electricity, magnetism, and optics. He took all these three concepts and he showed that by using these three concepts, he showed that light is nothing but it is an electromagnetic wave. Okay, this was the unification work made by Maxwell. Okay, and let us actually move to the third one. Just 1 minute, guys. Here, third one. Where it went? Yeah, here. Okay, third one. James, no, here. Because, see, Isaac Newton we discussed, Maxwell we discussed in the previous slide. So, this is the third one here. Okay. So, third one is given by Christian Oersted, very famous person, in the year 1820, and Michael Faraday in the year 1830. Okay. This was the third scientist who have made work on unification. According to Oersted and Faraday, they showed that electric and magnetic phenomena are inseparable. I'll repeat it again. Electric and magnetic phenomena are inseparable aspect of electromagnetism. Okay. Electric and magnetic phenomena cannot be separated. They are inseparable aspects of electromagnetism. That was showed by Oersted and Faraday. Okay, third scientist. Okay, that means third improvement or third unification work made by the scientist. Now let us move on to the fourth work. Okay, see here it is there, fourth one. Here, Glashow, Sheldon Glashow, Abdus Salam, and Stephen Winberg in the year 1973. Just 1 minute. In the year 1973, they showed that weak nuclear force and electromagnetic force, weak nuclear force and electromagnetic force, here I have written, weak nuclear force and electromagnetic force could be viewed as different aspects of single electroweak force. Okay, these two can be viewed as single aspect of electro weak force. Okay, this unification work they did. I'll repeat it again. They showed that weak nuclear force and electromagnetic force can be viewed as different aspect of single electro weak force. Okay, this was the work. That's it, guys. Now let's move on to the fifth one. Okay, Carlo Rubbia, Simon van der Meer, in the year 1984, they showed, that means they actually experimentally proved this one. Okay, they experimentally proved this one. What they proved? They experimentally verified, not proved, they verified. Okay, they experimentally verified that prediction of theory of electroweak force. Okay, this theory of electroweak force, they experimentally verified the prediction of this electroweak force. Okay, that was the fifth unification work. And after this one, okay, these were the five things. I will summarize again. First one is Newton, second is Maxwell, the third is Oersted and Faraday, the fourth is Glasgow, Salam and the Stephen, the fifth is Rubbia and Meer. Okay, these were the five scientists, and how they worked on unification we have explained. Now let us move on to the second content of this video. Okay, the second content is nature of physical laws. Okay, see the nature of physical laws. See, one thing we have to keep in mind, that facts in physics, no, the facts in physics are explained by taking a certain laws. Okay, any fact you take in physics, the facts are explained in terms of certain laws. Okay, gravitational law is there, no, gravity. Okay, gravity is one factor. Okay, and that gravity is a fact which can be explained through gravitational law. Okay, that means anything. Okay, a motion of an object can be explained through certain laws. Okay, any fact in physics, any fact in natural phenomena, in physics it is explained through certain laws. Okay, that is what we will study here. Nature of physical laws. What are their nature? Okay, we have mentioned here that some special physical quantities remain constant in time. Those quantities are called as conserved quantities. Why they are called as conserved? Because they remain constant. Okay, they cannot be created, cannot be destroyed. That is what is known as conserved quantities. Some physical quantities are there in nature. They will remain constant and they are called as conserved quantities. Okay, and in classical physics we will deal with the four kind of conservation laws: first, second, third and fourth. First, let us take up the first one, law of conservation of energy. Okay, I will actually read out this four: law of conservation of energy, then linear momentum, then angular momentum, then charge. Okay, so first one, law of conservation of energy. 1 minute. Here, law of conservation of energy. See, when law of conservation of energy comes into picture, what they have given is, in the absence of external force, just 1 minute guys, where it went? Yeah, here, this is the law of conservation of energy, first one. 1 minute. Yeah, this one. It tells that the sum total of energy of all kind in this universe remain constant. Okay, that means energy will remain constant, and energy can be transformed from one form to another. Energy can be transformed from one form to other, or it can be transported from one place to other, but total amount of energy never changes. Okay, this is what the law of conservation of energy tells. In simple words, we can tell energy can neither be created, it cannot be destroyed. Only what we can do is we can convert the energy from one form of energy to other form, or what we can do is we can actually transport the energy from one place to other. Okay, that's it what we can do, but we cannot create energy or we cannot destroy energy also. That is the reason the total amount of energy never changes, it will remain constant. That is what is known as conservation. Conservation of what? Conservation of energy, because energy will remain constant. First law. See, to explain this first law, we will take one example. Very famous example is there now. By what I will do is I will actually, this is one building. Let us actually, okay, imagine that this is one building. Above that building, one big rock is there. We will imagine like this rock. So what kind of energy will be there in this rock? Definitely, what will be there? Potential energy will be there. Stored energy. No, see, potential energy means what? Stored energy. And once the rock is pushed, it will fall down. No, when it falls down, the potential energy is converted into kinetic energy. Okay, because it is moving down due to gravity, it will move down. No, so potential energy is converted into kinetic energy. And what happens once it actually reaches ground? What happens? The kinetic energy is converted into heat and sound. Heat plus sound, the kinetic energy is converted into other form of energy, that is heat and sound. Okay, but total amount of energy will remain same. Okay, first it was having kinetic energy, the kinetic energy transformed into, I'm sorry, first it was having potential energy, not kinetic energy. First it was having potential energy, the potential energy was transformed into kinetic energy, and the kinetic energy was transformed into heat and sound. Okay, so the total energy of the system is unchanged. That is what is law of conservation of energy. Okay, second one is the law of conservation of linear momentum. Okay, see what law of conservation of linear momentum says. It says that in the absence of external force, the linear momentum of a system remains unchanged. That means if there is no external force, the linear momentum of the system will not change. That is what is law of conservation of linear momentum. If some kind of force is there, definitely it will change. If the force is not there, it will not change. Okay. See, this law means that in order to change the momentum, we have to exert pressure. That means force. In order to change the momentum, we have to exert force. We have to exert force, and the force should come from outside the system. Okay, because internal force will not work. The force should come from outside the system. Then only some kind of changes will happen. Otherwise, it will not change. That is what is given by law of conservation of linear momentum. Sir, you give an example. One example I will give. See, recoiling of gun is there, no? Recoiling of gun. That is one big. That is one best example of law of conservation of linear momentum. Okay, because in gun, what happens? Let us actually imagine this is one gun, pistol. Okay, gun. This one gun is there. Okay, here are some bullets, some design. Okay, here this arrow. Okay. So gun. Whenever we fire a bullet, what will happen? The law of conservation of linear momentum will be maintained whenever we actually fire gun. Okay, because when the gun is fired, force on the bullet inside the gun is equal to and opposite to force on the gun. Okay, whatever the force the bullet is going now here, this force is equal and opposite to force on gun. Okay, the force on bullet which is going forward will be equal and opposite to force on gun. That is what is known as law of conservation of linear momentum. Recoiling of gun, the example name is. Okay, whenever we fire a bullet, the bullet will go forward. With the same force, the gun will go backward. Okay, that means law of conservation of linear momentum is conserved there. Okay, that's it, guys. Next one, that is third one, law of conservation of angular momentum. Okay, see what is the meaning of law of conservation of angular momentum. See, to explain this one, now first let us read out what is there here. If the total external torque acting on a system is zero, angular momentum of the system remains constant. Okay, first we have to know what is torque, because they are telling, no, if the total external torque acting on the system is zero, if the torque is 0, the angular momentum, which is represented by this symbol L, the angular momentum of the system is constant. Only when torque is 0, it will be constant. But first let us know what is torque. See, torque is nothing but it is a measure of force. It is a measure of force which is needed to rotate which is needed to rotate an object about its axis. Okay, it is a measure of force which is needed to rotate an object about its axis is known as torque. I'll repeat it again. It is a measure of force which is needed to rotate an object about its axis is known as torque. And if the torque is 0, the angular momentum will be constant. That is what is actually given in this law of conservation of angular momentum. And we know that angular momentum is equal to inertia into angular speed. Okay, inertia into angular speed. See, rotating objects, no. The rotating objects will be having inertia. Okay, and also momentum associated with its rotation. The rotating objects will be having inertia and also the momentum associated with its rotation, and this momentum is called as angular momentum. Okay, that is what we have written here. The rotating object will be having inertia and also the momentum associated with its rotation, that is angular speed. Okay, and this is what is called as angular momentum. Okay, see, if we give one example, we will get a clear cut understanding about this law of conservation of angular momentum. See, planets are revolving around the sun. No? Okay, sun is their center and planets are revolving around the sun. Okay, here we can explain angular momentum, how the conservation of angular momentum is there. See, planets are revolving around sun in an elliptical orbit. To maintain their orbital plane, just 1 minute, orbital plane and angular momentum, they will keep constant. Angular momentum, both of them, they will keep constant in their plane. Okay, only then angular momentum is conserved. I'll repeat it again. The planets revolving around the sun in elliptical orbit will maintain their orbital plane and angular momentum in this plane constant. They will maintain both of them in constant. Who will maintain? Planets will maintain. While they revolve around the sun, they will maintain orbital plane and angular momentum. Both of them they will maintain constant, so that angular momentum is conserved. Okay, this is the best example for law of conservation of angular momentum. Rotation of planets around sun, because they will maintain no constant orbital plane and angular momentum, so that the conservation of angular momentum is done there. Okay, very easy and simple explanation. Now let us move on to the next one. So this is the last one, fourth one, and it tells about law of conservation of charge. It is not energy, it is charge. Okay, it tells charges can neither be created nor be destroyed, but only thing what we can do is it can be transferred from one body to another body. Charges cannot be created, cannot be destroyed. Charges can be transferred from one body to another body. Okay, that is what is told by law of conservation of charges. Okay, and we know that matter are made up of what? Matter are made up of atoms, and atoms are made up of what? Okay, atoms are made up of the electrons, protons, and also neutrons. Atoms are made up of electrons, protons, and neutrons. Okay, and if the object has equal number of electrons, that means number of electrons is equal to number of protons. If this condition is there, then the object, no net electric charge is there on that object. Okay, if the number of electrons is equal to number of protons, there will be no net electric charge on this object. One case. What if there is number of electron is greater? Okay, if there is if there is more electron as compared to proton, then the body is that means then this object is negatively charged, because there are more electron as compared to proton. Okay, this is case number 1. Just 1 minute. This is case number 1 and this is case number 2. In case number 1, both electron proton same, so there is no net electric charge. In case number 2, number of electrons will be more as compared to proton, so the body is negatively charged. And we can easily predict that third case, number of electrons are comparatively less as compared to protons, then we can tell that the body is positively charged. Okay, these are the things what are there in law of conservation of charges. Okay, that's it guys.